Hey guys, and welcome back to another lesson on set theory and Venn diagrams. I hope you joined us for our previous lesson on set theory and Venn diagrams, because today we're just going to focus in on some of the more advanced notation, set builder notation. So if you missed out on our lesson on set theory and Venn diagrams, I'll link it down in the description box for you below so that you can get yourself a good general overview of this topic. But let's just get into our set builder notation. Set notation and terminology that you should have already seen in our previous video includes the universal set symbol, the way we show a null or empty set, the curly brackets we use when we define or list the elements of any set, the symbol that shows set membership, the symbol that shows non-membership, the way we define elements which are not in a given set. For example, positive numbers and not positive numbers being negative numbers and 0. Now I'm going through this quite quickly because we've already seen it, but if you need me to go through this a little bit more in detail, have a look at that video down in the description box below. Let's move on to set builder notation now. Set builder notation is the kind of notation we use to define the set. So in this case, setting up set builder notation, I'm going to define set S. I always use a capital letter for the name of my set, and to define it or list its values, I need these curly brackets. In this case, I'm defining the elements of the set, and I'm using the variable x to define the members of the set. So I say set S includes all x's, where x is a year 11 student. Let's try another one, but this time let's define a number set. Capital A is the name of my set, and I'm using x to define the members of the set. Now, in this case, I'm saying that x could be any value that's a prime number. So set A is a set of all x's where x is a prime number. So here's what set A may look like. 2, 3, 5, 7, 11, and 13 are all prime numbers, but this could go on forever. So I'm going to need to put some sort of limit on the membership of set A. To do that, I could define the universe, so all values that I might consider in the sets. Here I'm defining my universe as being all values y, where y is less than 15, in which case set A could only include values up to, but not including 15. Now there are no more prime numbers that are less than 15, so I could then say that set A ends here. Set A is only the prime numbers 2, 3, 5, 7, 11, and 13. I could limit the size of my sets directly in my definition of the sets as well, however. So here's my set B, and I'm using the variable z to help me define the members of set B. This time I'm going to say that the values of z must be between -5 and +2. Do you know what this little line underneath the inequality sign means? That's the less than or equal to sign. So -5 is less than or equal to z, but z is less than 2, not equal to 2. That means that z could have a value of -5, but it could not have a value of +2. And this is the range of possible numbers in the set. Now I could go one step further to define the set even more. I'm going to say that z must be a member of these types of numbers. Now, I hope you know the different symbols for different types of numbers, but if you don't worry, we're about to go over that. This symbol here is the integer symbol. So this means that z must be an integer. Integers are positive or negative whole numbers. So including the value -5, z could have the values -5, -4, -3, -2, -1, 0, and 1. Not 2 though, remember why? Because this is not underlined. So here's my set B. They're integer values between -5 up to, but not including, +2. Knowing the symbols for types of numbers will be important for your set builder notation, so let's go over those now. And I thought it would be appropriate to do that in a Venn diagram. Starting here with the natural numbers. We've got 0, we've got 1, we could keep going 2, 3, 4, 5. These are our counting numbers. Natural numbers are whole numbers including 0. Then we've got Z, and we've just seen Z. Z is our integers. Integer values are whole numbers, but they're positive and negative whole numbers. You see out here, I've got the negative ones because inside the natural number circle is where all my positive numbers are going to be. But I've got no fractions and no decimal values in either of these circles. We have to go one more circle out for that. In the following set, that's the set of rational numbers. And rational numbers are the numbers which could be expressed as fractions or as decimals, which either terminate or recur. But this does not include irrational numbers such as the square root of 2 or pi or e. Those would, however, be included in our real numbers. Now, our real numbers include whole positive numbers, whole negative numbers, rational numbers, as well as irrational numbers. Our next set includes all of these types of numbers as well as imaginary numbers. These are our complex numbers. They're numbers which may involve both real parts, like 1, and imaginary parts, like the letter I, which we use to represent the square root of -1. Don't worry too much about that for now, because we're not going to deal with complex numbers. Now that we know our types of numbers, let's have a look at this next example. Set A is all values 2x, where x is less than or equal to 5, so that's including 5, and x is a member of, what's this symbol again? Those are our natural numbers, our positive whole numbers, including 0. So if x is less than or equal to 5, and it's a natural number, x could have the values 0, 1, 2, 3, 4, 5. That means that A includes all of the values 2x. That would be 2 times 0, 2 times 1, 2 times 2, 2 times 3, 2 times 4, or 2 times 5, which work out to be the numbers 0, 2, 4, 6, 8, 10. Notice that these are just the even numbers between 0 and 10 inclusive. But I've used set builder notation to define them. I could also use an expression to define the members of set B. Here I'm saying that set B includes all the values 2 to the power of A, where A are the members of set A. Now I've just defined set A. Set A are the values 0, 2, 4, 6, 8, and 10. That means that set B includes the values 2 to the power of 0, 2 to the power of 2, 2 to the power of 4, 2 to the power of 6, 2 to the power of 8, and 2 to the power of 10, which we can calculate to be the numbers 1, 4, 16, 64, 256, and 1024. So now that we've seen some quite simple examples and some quite advanced examples, let's see if we're ready for some practice. Here I've got two multi-part questions for you, where I either want you to look at some set builder notation and list the members of these sets, or look at these sets and try and find the rule that you could write for them in set builder notation. Go ahead and hit pause, copy the question, and give it a go, and hit play when you're ready to take it up. I hope you had a chance to hit pause, because here come the answers. Although set builder notation can be a bit complicated, I hope you notice that set A will be a list of odd numbers because it's 2 times some value plus 1, where that value is less than 4 and it's a natural number, so it's a whole number value including 0. So that includes 2 times 0 plus 1, 2 times 1 plus 1, 2 times 2 plus 1, and 2 times 3 plus 1. For set B, these are square numbers, where x is some value between 4 and 8, not including the 4, however, but yes, including the 8. So set B includes the values of 5 squared, 6 squared, 7 squared, and 8 squared. Next, for set A, notice that they are even numbers. They're not all of the even numbers, though. Where do we start and where do we end? Set A is 2 times some value, which is going to make it an even number, where that value is between 0 and 5, including 5 but not including 0. And that value is a natural number, so it's a whole number. So that's going to be 2 times 1, not including that 0, remember, 2 times 2, 2 times 3, 2 times 4, 2 times 5. You might have also written that as x is greater than or equal to 1, up to greater than equal to 5, or up to but not including 6. Set B, notice that these are all multiples of 3. However, they start in the negatives. So set B is 3 times some value where that value is greater than or equal to -2 but less than 2. And that value is an integer. It's a whole number value, but clearly we're including the negatives. So 3 times -2, 3 times -1, 3 times 0, 3 times 1, and 3 times 2. Set C, notice it's multiples of 5. But which multiples of 5? We'll say that set C is 5 times some value where that value is greater than or equal to 1, but less than or equal to 6. And that value is a natural number. It's a whole number. 5 times 1, 5 times 2, 5 times 3, 5 times 4, 5 times 5, and 5 times 6. Set D, notice what kind of values these are. That might have been harder for you to see. These are square numbers again, much like set B up here. But which square numbers? Set D are the square numbers where x is greater than or equal to 10, but less than or equal to 13. And x is a natural number. So again, whole numbers here. This is 10 squared, 11 squared, 12 squared, and 13 squared. Finally, set E, Miss Danielson Math, Mind Your Decisions, Mint Ace, and Brad Monto. I hope you came to the same conclusion as I did. Set E is the set of all x's, where x is one of my favorite YouTube channels. Now, how did you do? Hopefully you're getting the hang of this, and hopefully you got that question E right. If you did, thank you. I love you guys too. Till next time, keep practicing, and I'll see you soon.